Hello, my name is Rocio Daniela Pico Costello. My ID number is A01741296, and today I will be presenting mini challenge number 3, which consists of developing a kinematic simulator for this robot, which will be based on this mathematical model, which is x dot equals v cosine of theta, y dot equals v sine of theta, and theta dot equals omega. And this we're going to model it in Python. So here is my code. It was based on a previous example given by the teacher. And yes, it was developed on the template. So the first step was to import all of the libraries that we were going to be needing, which are all of these, and sampling the variables that we were going to use, which is the start time, current time, last time. We're going to set those to 0. Also the v and the omega 0, and the transform functions will all set to 0. And the next step was to declare the messages that we were going to be using, which was, of course, the transform and the odometry. And okay, now we initialize the messages if required, and transform the angle into a quaternion for the orientation with this function over here, which is quaternion from Euler. Now we define the callback, stop condition, initialize the setup node. This was all with teacher template. Set the parameters, set the initial conditions for the system, all 0 because it's a float 32, so it's 0.00. Configure the node, set up the subscribers, the publishers, and the broadcasters. And now we get to run the node. So first we open the while loop. We establish this for start time, current time, and last time. And now we set the dynamical system simulation, which is over here. And dt is, of course, the sample time. Here we set the previous mathematical equations that we discussed. Here they are, but set to programming. And now we publish the transform message, which is the pose of the robot. Here it is for translation, and here it is for rotation. We publish it. And now we do the same, but for the odometry message. So here it is for everything, but precision, orientation, and linear and angular twist. So now that we finished that, we just publish the odometry and close the while loop. And now we go to the terminal. You can see I was already trying the code. So for here, we have to catkin make and then source, but I already did that, so I'm not gonna do it. And now we Rust launch the file where it is located. Here it is in the catkin workspace. So we launch it and we open our Vs. Here it is opening, and we're gonna see the robot here, and we are gonna have this to make it move. So as you can see, the robot does move and it does turn, but it goes very, very slowly for some reason, probably something that needs to be debugged. But we are going to try to make it work. I'm going to increase the velocity of the turn. Here it is already going too far, so you can see. But we're gonna try to make it move. Oh, here it is going backwards and forward and moving around. We're gonna increase the turn and try to make it move. Here you can see it is moving. Yes, it is a little bit slow, but it is moving. So it's definitely something that needs to be debugged. But we can see that I was able to see the simulation for the robot, which is the most important. And we can see that it does work. So technically, there still needs to be some debugging, but the majority of the challenge was completed successfully. And there's still some features that need to be checked, but mainly it was successful with a little inconvenience. But it's all part of learning. So that's it, and thank you so much.